Friends, this is a video summarizing a few aspects of the introduction of thermodynamics, specifically temperature, Maxwell-Boltzmann distribution, the ideal gas law. To begin, let's look at a Maxwell-Boltzmann distribution. What that is that when you have a bunch of particles in a box, I was looking for my annotation tool, right? They're flying around in different directions, bumping into each other, and they're all colliding, exchanging energy, where some of them will go fast, and then some of them will go slow, and then they're going to bump around, exchanging energy, but of course, the energy is conserved. The energy is conserved is because we want them to collide elastically, or at least those are the assumptions that the ideal gas model of thermodynamics is based off of. So thermodynamics, we have to remember, is statistical. Statistical mechanics. And any thermodynamics course you might take in college is actually not called thermodynamics, it's called stat mech. It's called statistical mechanics. And it's intensive and beautiful, and it's statistical though. So you're going to do statistics of an enormous amount of balls, particles. They're modeling them as little tiny things, very tiny relative to the size of the room. They're a very large amount moving in random directions. They collide elastically, so kinetic energy is conserved, and they don't interact in any other way, which of course isn't true, but for a gas is a good assumption. For a liquid, you now have potential energy chemical bonds, and solid, those bonds are even stronger. But for a gas, they're just flying around hitting each other is the model, and it works really well as a model, which of course then speaks to the grander truth of a gas, that there aren't many forces involved. It's the temperature that is their motion, which is the whole point. The average temperature, the average kinetic energy is related to the temperature by this equation. This is for a monatomic gas. For a diatomic, we want to be very, 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 very sure that we know that this is only for a monatomic gas. For a diatomic gas, Ke average is 5/2 kBt. This 5 and this 3 come from something called the degrees of freedom, which I'm not going to get into, but you would get into if you took a stat mech class, right? That's something I'm just going to give you. The whole point is a diatomic molecule has 2 more degrees of freedom than a monatomic molecule because it can vibrate back and forth, or it can rotate like that. So there's more ways it can have energy. So its average energy is greater per its temperature. So temperature is a statistical quantity. In order to have temperature, what you need to have is something called a Maxwell-Boltzmann distribution. So what a Maxwell-Boltzmann distribution is, how can I clear everything? Perfect. Is when there we go. These molecules are not going at the same speed. They're all going at different speeds, but the speed fits a model very predictably, where the speeds equalize. Some are slow, some are fast, to something called a Maxwell-Boltzmann distribution. And you might notice that 100 Kelvin, right, and that's the temperature, we want temperature to be in something called Kelvin, right, that's how we relate And that for the Boltzmann constant is this value. So if you're taking notes for the first time, you're just going to put the things I did in boxes. You're going to write the 5/2 kBT, this, that temperature's in Kelvin, maybe a little draw this diagram right here, where we have V1, V2, V3, and V4. And notice what happens is that if something is heated up, like heat conduction, right, is the transfer of kinetic energy via collisions. To heat up a room, you have something going fast in the corner. We call that a heater, right? That was boiled water. It's going fast. And that collides with the air molecules and makes them go fast. And eventually they collide with your skin and your skin vibrates a little faster. That's called heating up, right? So temperature is the speed of the molecules. But the speed of the molecules is not exact. It's in a Maxwell-Boltzmann distribution. So if I'm graphing the speed and how many particles are going at that speed, notice at 100 Kelvin, they're not all going at V1, but some are going slower, some are going faster, but there's an average peak velocity. And then if I heat it up, if I then transfer the kinetic energy via heat conduction, right, then it goes faster on average, and the graph widens with increasing temperature. The area of the curve, the total number of particles stays the same, so it just gets wider. Some still go slow, because again, every time you have a collision, there's always a slow one at the end. There's a greater probability of finding faster molecules in hotter gases. And I keep heating it up. Now look, I have a bigger peak at V3, and then I have a bigger peak at V4, et cetera, if I go from 100 to 300 to 600 to 1,000 Kelvin, right? So that's just making the molecules go faster and faster. Now, let's take a step back. And let's kind of review and then go to step 2. That first of all, temperature is in something called Kelvin. It's related to the average kinetic energy. For monatomic and diatomic, it's different. Kelvin is Celsius plus 273.15 by definition, because they wanted to relate it to Celsius. And it's related, and therefore that determines the Boltzmann constant, where the kinetic energy average is 3/2 or 5/2 kBT. This is monatomic. What's a monatomic? Like helium, argon, right? The noble gases, right? They only exist on their own, but 5/2 for a diatomic, such as oxygen, like we're breathing right now, or nitrogen, right? Or hydrogen, H2, etc. So our air, for air, we would use KE average is 5/2 kBT, where KB is the Boltzmann constant. It's 1.38 times 10 to the negative 23 joules per Kelvin. Great. That's where we're at so far. Now, the whole point is that temperature is speed. It's the average kinetic energy, and it fits that Maxwell-Boltzmann distribution. So we need to have a lot of particles to have a temperature. There's no such thing as the temperature of a single particle. Temperature is a statistical quantity that's only established once they've reached the Maxwell-Boltzmann distribution. It's called thermodynamic equilibrium. So once a room has equalized and you have that distribution, now you can say there's a temperature. And it comes from their average kinetic energy from this formula. Put it in a box. Now, more importantly, we derived this in class. I'm going to kind of skip ahead just to the result. If you turn n particles, right? So now we have n of them. Instead of just, looking at the average, well, n particles will have a total kinetic energy of n times the average, right? And therefore, what we can do is say, okay, well, n particles is the number of moles times Avogadro's number, where Avogadro's number is a mole, is 6.02 times 10 to the 23 molecules. and is defined as where one atomic mass unit equals 1 gram. Sorry, 1 mole of atomic mass units equals 1 gram. That's what Avogadro's number is. It turns the periodic table, for instance, O2 is 32 grams per mole. If you look at a periodic table, oxygen in and of itself is 16 grams per mole. The whole point of this grams per mole thing is that if I have a mole of them, there's 16 grams. If I have 16 grams of oxygen in my hand, that means there's literally this many molecules, which is extraordinary. Kind of gives you like the idea of how many molecules there are like in your hand right now. 10 to the 23. That's what we're talking about. That's how many molecules. You can kind of zoom in and realize that's what's going on in the room, right? Is it's on the order of that many molecules in your hand, like if you were to hold it as a ball of air, or even your hand is made of that many molecules on the order of something like that. So the total number of molecules is the number of moles, N, times Avogadro's number, which is that. So if we plug this into here, we get that Ke total is going to be the number of moles times Avogadro's number times Boltzmann's constant times the 3/2 or 5/2, depending on if you're monatomic or diatomic, times the temperature. But if you multiply these two together, you get 8.31 joules per mole Kelvin, and we call that the gas constant. So this is where the gas constant comes from. It's just Boltzmann's constant times a mole, which is kind of cool. So here's where our next formula comes in. Ke total is 3/2 or 5/2. Careful to use the correct one, nRT. And in class, we proved the ideal gas law, right, which is PV equals nRT. If you missed that derivation, it's okay. I'm going to give a quick summary right now. Where it comes from is that you have a bunch of particles in a box, and when they hit the walls, they exert a force. They bounce off and they exert a force, or when they hit each other, they exert a force on each other. So the force on walls or each other creates a pressure. It manifests in a pressure. The collisions, right, with the walls or each other creates a pressure. So remember, it's all about collisions. How is heat conducted? Heat is conducted via collisions. So I drew that in the other one. Heat is conducted via collisions. Pressure is pushing via collisions, right? So what affects these collisions? Well, what you want to look at is two things, right? What affects collisions? And therefore the pressure. One, the rate of collisions, or the time between collisions. So if you have a bunch of molecules, right, how often are they bumping into each other? If you have a piece of paper trying to fall and you keep hitting it up, it's going to push up. That's a pressure. But if you do it very sort of like haphazardly or a long time between, it'll clearly just fall down. So you can see how the rate of collisions determines the total pressure. Remember, it's a statistical quantity. So we're averaging this over time, but the molecules are hitting like 1,000,000 times a second. That's different from them hitting 2,000,000 times a second. That's more pressure averaged over time. So remember, these are statistical quantities. So what affects collisions? The rate of collisions, and of course, the speed, or literally the energy. That's what I mean. Or you can think of it as the momentum. Same thing. So if the molecules are moving faster, meaning higher temperature, the energy per collision will be grander. The force per collision will be greater. So it's not just it's how often they happen, and it's the momentum or the energy per collision. Obviously, if each collision has a greater oomph, greater energy behind it, there's going to be a greater pressure. So how does this work? Well, this is the whole point. Pressure is the outcome. You can't just increase the pressure of a room. I can increase the size of the room. I literally just move the walls out, or I move them in, or I can decrease the volume. I can put more molecules in. Here you go, more molecules. I can increase the temperature by heat conduction, which is via collisions. Those in turn affect the pressure. So pressure is the outcome in this equation, right? And hold on, let me undo that box. It's what makes things happen, right? Via a pressure gradient. Remember, we talked about pressure gradients with buoyancy force. There was more pressure on the bottom of an object than the top. Therefore, buoyancy is created. That's the whole point of buoyancy. So this is called a pressure gradient. So we're going to look out for these in our examples. And I think the examples hopefully will show this, but the whole point is conceptually, this is going to, 4 weeks, the next 4 weeks, we're going to basically be returning to this exact thing I'm boxing right now, right? Pressure is the outcome. It is what makes things happen via pressure gradient, which creates a net force. So, and I'll give you an example in a moment, right? So again, you can pause the video if you need, but I'm going to keep going. So PV equals nRT. First of all, let's identify that. And then we have KE total equals 3/2 or 5/2 nRT as well. Notice that they both have nRT in it. So I could probably just plug this in there and I can get 3/2 PV, same equation, which is kind of cool. I'm asking you to do that on your homework. Let's see if you can figure that out. Right, these are in pascals, which is newtons per square meter. Careful, not ATMs. So if I give you like 1 ATM, you have to convert to pascals. 1 ATM is 101,325 pascals to be exact. I'll give that to you in class another day though, so you might see that, but there it is. Volume is in liters? No, cubic meters. N is moles, number of moles. R is 8.31 joules per mole Kelvin. And temperature is Kelvin. There you go. There's your units of all your statistical quantities: pressure, volume, number of moles, gas constant, temperature. There it is. So what's the point? Well, how to change pressure. So if I change volume, for instance, increase volume, what does that do? Well, increasing volume will decrease pressure. Why? Because there's more space. More space. And this was in the derivation, and I'm sorry that if you weren't there to see the mathematical derivation, I thought that really helped, because the whole point, if there's more space, you can imagine a ball going back and forth. If there's more space, it takes it longer. The molecules are more spread out. So are they going to collide more frequently or less frequently? Well, clearly, if there's more space, there's fewer collisions. That's it. It's that simple, right? So keep it simple, because more space means fewer collisions. So increasing volume, careful, this is volume, I said velocity. Increasing volume decreases the pressure. Now, obviously, I can change the number of moles. Increase the number of moles will, of course, increase the pressure because more collisions. Same thing, same idea behind, if I have more molecules in the same amount of space, they're going to collide more often. Only I'm changing how many there are, not the volume itself. And you're seeing this is related to density, which is kind of cool. And then I can change the temperature, where an increase in temperature increases the pressure. Why? Well, two reasons. Because remember, temperature is speed. So if temperature is speed, the concept of it's literally kinetic energy by this, right? But what is that? Kinetic energy conceptually is speed. So conceptually, something is hotter means it's going faster, right? The molecules on average, their Maxwell-Boltzmann distribution is now at a higher peak velocity. They're going faster on average. So if I increase temperature, I'm increasing pressure because why? Well, faster, here's why, is the whole point. But what does faster do? It both makes more collisions, because if they're moving faster, they're going to collide more often. And more, now here we go, energy per collision. Remember, there's that second part there. So for temperature, it's kind of fun because temperature actually affects both, and it shows up in the derivation of PV equals nRT, where when you're doing it, you realize that the speed not only creates more change in momentum per collision, because if two things are going faster, boom, right? There's now more energy per collision. So imagine a ball going really fast at a wall, boom, 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 and a ball going really slow at a wall. Clearly, the fast one's going to exert more pressure, and it's going to collide more often. So it's both makes more collisions, right? Makes more collisions. Sorry, I'm trying to write clearly here. Makes more collisions and more energy per collision. That's it. Now we're ready to do examples, right? So here's our examples. Right, so let's say we want n equals 1 of helium gas at T equals 300 Kelvin. What is the total energy? And what is the volume at atmospheric pressure? So this one's pretty easy. Hold on, I'm going to get my calculator. And all we do here is now just use the equations, which is nice, right? So now it's just can use the equations. So notice I wrote just E total. E total is KE total. I'm just going to not write the E, because remember, we're dealing with a gas. Gas has no potential energy, and we're ignoring gravity, because it's just we're saying they're flying around the room, right? So there's no MGH, it's none of that. MGH just creates hydrostatic pressure, which I know we didn't really go into, that hydrostatic pressure is kind of like potential energy, but we're ignoring hydrostatic pressure. We're just talking about the pressure via collisions. We're only focused on the collisions. We're only focused on the gas kinetic theory part. That's everything in the ideal gas model. That's it. And it's sufficient. It's like all we really need. If we added hydrostatic pressure, added like a liquid phase change and stuff, there would be specific heat involved. There'd be the other little intricate things, but really this gets the job done most of the time for what we're going to end up using this to prove and to invent and to discover and to apply it to. So anyway, let's just start. Simple question. I have a mole of helium gas at this temperature. This is about 27 Celsius, which is a nice like 80 degrees, something like that. What's its energy? How much energy does it have? And what's its volume? How much space is it taking up? Is it huge? Is it the room? Is it just like a little fingernail? Is it like a liter? How much? Let's figure it out. So first of all, KE total, E total, again, will be the same thing. Will be 1, sorry, 3 halves or 5 halves. 3 halves because helium, it's monatomic, right? Times 1, N, times R, 8.31, times T, 300. Boom. What do I get? I'm going to do that. 0.5 times 8.31 times 300. 3,739.5 joules. Okay, or 3.7395 kilojoules. I don't know if I have a good idea of that type of number, but we will later. Later, we're going to try to make sense of these numbers and like, is this a lot? Is this a little? Well, this is just a mole of helium gas. So maybe this is like a normal amount of energy for a gas. Maybe we'll start there. This is kind of normal, right? We'll sort of see how this changes as we go through different examples. So just, all right, cool. We're in the thousands of joules. Right on, right? Right. And those of you who know, you know, food wrappers in Europe, you realize that they do theirs in kilojoules, right? A calorie is, I think, 4.184 kilojoules. So this is like food you eat. It's like level energy, right? Cool. So we're realizing this is kind of a normal amount of energy, right? Just sort of getting a scale involved. So how do I get volume? So that's 1. What's 2? Well, PV equals nRT. So 101,325, that's atmospheric pressure. Pascals, that's given. That's atmospheric pressure, right? You should have that in your notes. I know I said 101,000, but let's be accurate. I'm going to add the 325. Right, we'll be accurate, right? Times volume in cubic meters. We're going to get cubic meters here equals nRT. So then I solve for V. V is going to be, let's do it, 8.31 times 300 divided by 101,325. I get 0.0246 cubic meters. And if I do 1, 2, 3, that's going to be 24.6 liters. There we go. 24.6 liters. And I know standard temperature and pressure, I think, is atmospheric pressure. I don't remember what standard temperature is, but you get something like 22.4 liters. And we can do a simple ratio. I just realized, because if PV equals nRT, we're going to do this mainly next week, but might as well start now, that if I just change the volume and the temperature at same pressure, so same N and P, then you might notice that V1 over T1 equals V2 over T2. Those are directly proportional. Right? More temperature means more volume. Why? We're going to think about that in class. I might make another video about that, but I'll say stay tuned for the why. Think about the why. So just mathematically, though, what do we get? Well, we get that, okay, 300 over, what was it? 24.6 over 300. Equals 22.4 liters over T2. And again, I can use liters. I don't have to use cubic meters in a ratio. So for ratio, we're going to realize units don't matter as long as they match, which is nice. So you don't have to deal with all those decimals. But the equation, we have to use joules. We have to use cubic meters and pascals. But here you go. So that divided by 300 divided by 22.4, and I get oh. To the -1. Cool. I get T2 is 273.15. Does that mean 0 Celsius is standard temperature? What? Cool. I just learned something. All right. So I just wanted to connect this with something you might have learned in chemistry. You might say, where'd I get that from? Well, I know 22.4 liters is like a standard volume that a mole of gas fills. at a certain temperature, and that temperature happens to be 0 Celsius. Whoa. Anyway, so that was practice using the equations. Again, pause this, rewind if you need to go through. We're going to talk about the mechanism in class. I hope to post another video about that, but either way, we'll cover it somewhere along the way. Have a peaceful day. Bye, friends.